Now, all of that was with regard to the security of a system. One of the other choices that you need to make when you are looking at a production deployment is the fact that Linux, as we know, is a full-blown operating system. It basically provides a file system interface, and more importantly, the entire set of drivers, applications and so on occupy a fair amount of space, which means that you need some kind of a file system within which you can unpack all of these different drivers, applications and so on, right? Which means that there are a few different choices that you need to make with regard to file systems. Now, those of you who have installed Linux on your laptop or desktop might have seen that by default the file system that comes up is something called ext4. It's called the extended file system, basically version 4. It's a full featured file system with pretty good performance overall. The problem is it is not optimized for so-called flashware. Okay, what does that mean? It means that flash memory has a problem of something called wear leveling, meaning that it has a limitation on the number of times you can write to a given set of locations in the flash memory, right? Now, the ext4 file system was created originally for so-called spinning disks, right? The hard disks which actually had spinning magnetic platters and heads that would read from them, not really for SSD devices at all, and let alone that not for eMMC devices which actually don't have the kind of behavior patterns that you find in magnetic disks at all. Okay, so they have good performance, but they are not really aware of what happens in terms of wear leveling and so on, which means that if you have an eMMC card, which is the kind of card on which that is commonly used in embedded systems, right? It's directly sort of soldered onto the PCB usually. Many of those cards have built-in wear leveling, right? Meaning that they would actually at the hardware level sort of try and make sure that data is moved around to different segments of the system, so that you don't do too many writes in one particular block of the flash memory, right? The risk being that, especially if you have a file system like a temporary file system where there's a lot of writing going on, you might end up essentially negatively impacting one particular block of the flash memory while the rest of it is actually perfectly fine. But wear leveling, what it tries to do is it keeps moving that around, so that even if you are trying to write to one particular block, at the hardware level it sort of moves it and says, okay, you think you are writing here, it's sort of like a virtual address translation, it actually writes somewhere else and keeps moving that around for you, right? So if you have an eMMC with hardware wear leveling, then yes, ext4 works well. But there are other file systems that are probably more useful in the context of embedded systems, where you are extensively going to be using flash and not directly spinning disks or something else of that sort, right? There is another file system called squashfs, which you might have encountered, for example, in certain it's used in essentially to create one combined file system which can be used for, let's say, booting. And if you have booted something from a pen drive, then a version of the squash file system is probably what is being used in order to store the data which is present over there, right? There are a couple of different ways of doing it, but the squash file system by itself basically allows you to put everything together into a single file system. What is usually done in the ISO files is a variant of that, so it's not really correct to call it a squashfs, but the idea is sort of similar, right? The main point of a squashfs is that it is read-only. You have already sort of compressed all the files together into one big file, right? All that matters is inside that big file there is enough information that you can access any sub part of it. The point is it can be very fast for reading, but you cannot modify it, right? So usually if you have a squash file system, what is done is that it can be used for the production read-only root. What does that mean? Your root file system which contains your applications is read-only. You don't need to modify any part of it, right? And this is a good use case for something like a squash file system. It's compressed, it's fast, right? And you are not really writing anything, so wear leveling and so on doesn't really play a part in it. It's a good way to have the root file system of your embedded platform, okay? But it is read-only, right? So instead, if you want to have something which is read and write, there are other operating file systems. One of them is called the UBFS, right, which is designed for raw NAND, not the eMMC type, things which do not have wear leveling built into them. The file system itself takes care of wear leveling and handling bad blocks and so on, right. So this can be a potentially good use case for something which allows both read and write into raw NAND based storage. Right. And finally, there is also very often in most of these embedded systems you will find now, and including in laptops these days, you will find that there is something called the tempfs, right. Linux basically by default tends to have this folder called /tmp, which is for temporary files. There are also some folders like /var log, which store log information corresponding to what has happened since boot up. These are not essential to retain across reboots, right. So they can be useful, but it's not essential. So what happens is that very often the choice is made to just store them directly in RAM, not even on an actual disk, which means that they are extremely fast. There is no flash wear and no wear leveling required over here, but the problem is it's going to be lost on reboot. What all of this together means is that very often when you are dealing with building a production system, you want multiple different things available there. You want a read-only root file system. SquashFS is perfect for that. You want some kind of an overlay which is writable, where for example you can copy new files, you can sort of store temporary data, you can use it to write some programs and so on. That could be UBFS or ext4 depending on the kind of storage, underlying storage that you have. And in general most systems would have a volatile temporary tempfs file system as well. So when you are building a full-blown Linux environment for something like this, you want to sort of decide on the kind of file system pattern that you are going to use, the layout that you are going to finally be using in practice. Now, file systems play another important role, which is also related to how you can do an update. Remember what I said about a read-only file system being used for the root partition. What happens when somebody wants to update the system, right? And you are probably used to either a Windows system where it says download all these patches, apply and reboot or something like that, or Linux where you do maybe an apt update, a whole bunch of new packages are applied, and sometimes if depending on what has been changed you might be asked to reboot the system. The problem is embedded systems suffer from two issues, right? One is you don't want to keep rebooting the system, and secondly you might actually have deployed this somewhere out in the field where you do not have physical access to it at all, right? So reliable field updates, meaning that after you have deployed it in the field, you need to be able to reliably update it, and this is important for systems. One example that you might see is there are some of the TVs tend to have a lot of fairly complicated software in them now, and occasionally they sort of download an update, right? Now the point is, if something goes wrong with the update, you can't pick the TV up and carry it to the showroom and ask them to repair it, right? So they need to make sure that the updates are absolutely perfect. You can't suddenly go plug in a new sort of device, you don't have a keyboard. If it was Windows, you can always do something and try and recover from it, maybe uninstall a few patches and so on. You can't do all that with a TV. So what do you do instead? Most systems use what's called an AB partition scheme, right? A partition is essentially, you have disk space, some kind of storage, and there is something called a partition table that basically says, okay, this storage needs to be used in a certain way. There is one part that needs to be used for something, there's another part that needs to be used for something else. You might already be familiar with it in terms of the different files that are created when you install a new OS. In terms of Windows, you probably have just come across the C:, it's the single partition, but there might be a D:, maybe a recovery partition that's present somewhere in your file system, right? But that's on a laptop or a desktop. On an embedded system, what's usually done is that you have very often two separate partitions. They're called the A and B partitions, right? Normally the device boots from partition A. When you are updating the system, whatever software is downloading the update writes a new image onto partition B, which is currently not being used. It then marks B as bootable, but it also marks A as the fallback, right, and then reboots the system. What happens in that scenario is, by default the system will try to reboot into partition B, but it will have some kind of a fallback mechanism, maybe a timeout or something, a counter which keeps track of whether it is being rebooted too often, and it will see, was there a successful boot into partition B? If so, partition B can probably go in there and mark it saying, okay, this was a successful update and you need not sort of you can ignore the fallback option. But if it doesn't do that and the system reboots again, it notes that, okay, I tried booting into B, somehow that doesn't seem to have worked, let me revert to partition A and boot back from there, right. This kind of setup, this AB partition scheme, is what's called an atomic update. It makes sure that the entire update either succeeds or fails. You don't end up with a system where some of your packages updated, some did not, your OS ends up in a broken state. Either everything works and you are now booting from partition B, or the entire thing is rolled back and you continue with partition A. Okay. So you always have a working fallback, and this is critical when you are talking about field updates, especially for remote systems, but even for any kind of general embedded system that you have. Now, atomic updates are, what they try to do is that the entire update either succeeds or fails. You write to an inactive partition, verify, checksum, flip the boot flag. If something failed midway through, right, you basically end up booting back with the old system, right. Now, the problem is, an OS with all packages, drivers, applications and so on can end up being several gigabytes. You don't want to keep downloading that much because maybe the changes were relatively small. So then there are the notion of so-called delta update, right, where essentially what you could do is transmit only the differences. This becomes crucial when you are actually talking about remote systems that can only be reached either over a cellular network or potentially even over a satellite based communication network, right. Things like OS tree allow you to do what are called partly immutable systems, where essentially there is an underlying operating system that is unchanged. You can unpack a set of differences on top of it and it will now reboot with those differences. But it is always possible to reconstruct without much work the exact image that was being used earlier, right. So the fallback is possible. The problem is it's a bit more complex because these are now forming sort of overlays on top of an underlying operating system, right. But it can, if done properly, it can result in a significant reduction in the required bandwidth for the system. Now, all of this was with regard to how you sort of store and provide updates and so on. What about the kernel itself, right? When you are actually dealing with a production system, you want to have something that is fairly well optimized for the kind of scenario that you want. One of the choices that we have talked about with regard to device drivers was, so far all the examples that we considered was where we wrote the device driver as a module. It is possible to take that module and build it directly into the kernel. So when we type make VM Linux, it actually goes in there and compiles the driver in, and rather than making it a module, it makes it permanently a part of the kernel. Now, why is that a good thing? It means that it is always loaded, the boot time is faster, right? Whereas the module will be loaded only on demand, which means that the actual VM Linux could be slightly smaller and the modules themselves have gone into the init RAM disk. Of course, if you are then going to compile the init RAM disk into the VM Linux the way that we did for the examples, it probably defeats the purpose of having a module, but that's not how it's usually done in practice, right? That was just an example that we used to make life simpler for our demos. In practice, usually you have a VM Linux that is small. The initrd, initramfs, is a separate file that is loaded later, right? Now in production, what you always want is that critical drivers, for example the console, the UART or whatever it is which gives you the basic output information, you always want it built in. But pretty much anything else you would try and have it as a separate module later. Okay. Apart from the modules, right, another thing that can be used for size reduction is in general disable any unused features. We looked briefly at this problem of how to do kernel configuration, but there are literally thousands of config operations, and going and tuning every one of those is actually quite difficult. It's not a very straightforward thing unless you are really fully aware of what's happening inside the kernel. Right? You can also do certain other things, like for example stripping out debug information using compression, which can actually sort of reduce the size of the kernel image. Of course, once it's loaded into RAM, it needs to be decompressed, but on disk it can have a lower footprint. Right? And of course, use just the smallest init RAM FS that you can with just the drivers that you need for the basic system that you are building. Right? So all of these help to sort of do size reduction, right? And you can get something like, a few megabytes. The default would be like tens of megabytes. You can probably bring it down to something like 5 megabytes for a minimal Zinc kernel. Now, these are just indicative numbers. It's not like, you can actually go in there and say, okay, it came out to be 6 MB. Why did you say it should be 5? I'm just sort of giving an order of magnitude estimate out here. You can potentially bring it down by a significant factor by stripping out all the unnecessary things that you do not need. Similar thing happens for boot time, the amount of time required, right? A typical boot system might take tens of seconds. You could bring it down with heavy optimizations down to 2-3 seconds. How do you do that? Once again, reduce the type of init RAM FS that you use. There are ways by which you can parallelize the different tasks that need to start up at initialization, right? Just reduce the number of messages that scroll on the screen, right? Use the quiet kernel parameter to reduce the amount of log messages that come on the screen, because printing is actually a slow process, even though we don't think of it that way. Disable any unused hardware, because what happens is if something is present in the device tree, an entry gets created for it and then the kernel tries to probe the drivers, right? Don't do that. Disable them, have whatever, just the minimum that you actually have on the system. U-boot also tends to have, specific parameters such as a boot delay, which is there intentionally because it basically allows you to sort of interrupt the process and say, look, I don't want you to boot from this. I want to type in some extra information and change the way that the system is going to boot, right? So there are a number of optimizations that you can do when you are actually going for production. All of these things like boot delay equal to 0, not having quiet as a kernel parameter are there because the assumption is that you are still working on the system and you are trying to debug it and improve it. During that time, you do not want to do these kind of things. Only after you are sure that this is actually going out to production, at that point there is no point in having a non-zero boot delay and so on.